Great.
Okay,
okay, cool.
Right, then we're all set. So we're ready with to start with our first talk of the afternoon session. So Katerina is going to start talking about work and heat. Please go ahead when you're ready.
Well, thank you. So hi everyone, thank you for being here. I'm right now a postdoc in John Gould's group at Trinity College Dublin, but the work that I'm going to present here today is actually based on my PhD that I did with Klaus von Aarhus University. And I'll be talking about work and heat in conventional and measurement-powered quantum heat engines. So first of all, well, there are many ways of building a quantum heat engine, and many of those have been studied. But we decided to focus on a thermoelectric engine because it can be used for energy conversion devices, and because the work is produced by an electric current that can be measured experimentally. And the system that we worked on, we actually based it on a system that was first proposed by Potts and others. And you can see the reference here to their paper. And well, here is the reference to the paper that we wrote on this work. So our system consists of two superconductive qubits here, a hot side and a cold side, and each are coupled to a heat bath with a coupling constant kappa, and they're connected by a Josephson junction with the respective couplings. And we set the system to DC voltage, and we impose the resonance condition, which means that for each quantum heat that is transferred from the hot to the cold side, there's a passing of a Cooper pair across the junction. So first I will tell you about this system as is, as I just presented it, how we characterize it, and how we calculate the work and heat mean values in fluctuations, which is actually the interesting thing that is the challenging thing to calculate in this quantum thermodynamics setups. And then I will tell you a little bit about how we use the tools that we employed in calculating the work and the heat in looking beyond the average values of those properties and look into the dynamics of the energy transfer between the different parts of the engine. And then I will tell you about a modified version of the engine where we replace the heat bath by a measurement protocol. And we'll tell you how we did it and how the measurement protocols that we consider to actually have a positive work production by the engine. So let's start by the heat bath powered engine. So here it is, the same as I just presented you. And for this engine, we can derive a Hamiltonian rotating wave approximation as a function of the polyspin operators for the excitation of the qubits. And since we have this resonance condition, the current is actually directly linked to the rate of the excitation of the cold qubit, as we can see here. And then if we actually restrict ourselves to the case where those the coupling constants to the bath are equal, which we did to have a simpler and more compact analytical expressions, we can directly derive the steady state current, the average value of the steady state current in the system as a function of the occupation of the bath. And here EJ prime is just this EJ times the coupling constants to the junction. And then to study the dynamics of the system, we solved the master equation, local master equation, where you can see here the Hamiltonian part and then the dissipative part. And we made sure that the values of our parameters were well within the range of the application of the local master equation. And so with that in hand, we wanted to see if we could calculate first the average values of the work and the heat. And we placed ourselves at 0 Kelvin, because then we were in a situation where the excitation of the cold qubit meant that 1 quantum of heat was transferred through the junction, and actually the cold bath could be considered as a heat detector, which is important then for the next part, for the fluctuations. So for the average values of the work and heat, well, we can directly get those values by taking here for the work the steady state value of the current times the voltage, which is basically just the electrical power, and we multiply that by the integration time. As for the heat, well, since we are at this 0 Kelvin, the heat that is transferred through the engine is directly linked to the excitation rate of the cold qubit times the energy associated with that quantum times the coupling constant to the bath and the integration time. So then we want to calculate the fluctuations. For the work fluctuations, we actually define the integrate current, because our current is a continuous variable, and from this expression we could directly calculate the variance of the work using the classical the formula for the variance. For long integration times, we obtain this expression, where you can see that it is actually a function of the 2-time correlation function of the current. And the way we calculate these, so we started in the steady state, and then by using the quantum regression theorem, we started in the steady state at t, then we let the system evolve, and then we measure the current again at a later time. Then we asked ourselves the question about the heat. And for the heat, it wasn't as straightforward as for the work. And the way we derive these, the expression of the fluctuations of heat, is by using that fact that our cold bath can be modeled as a heat detector. So we use the expression for the quanta arriving into the cold bath, and we calculate the fluctuations of this quantity, and then we relate that to the variance, to the fluctuations of heat. And to arrive to this expression, where you can see that we also have the 2-time correlation functions that are involved, we had to rely on globose with a detection theory. So it was so we did really need that model of the heat of the cold bath as a heat detector. So that was an interesting result for us, because we're talking of heat, but using very tools from quantum optics to actually derive that thermodynamic property. And if we look at the behavior of heat, we can see that it has a sub-Poissonian behavior in the number of quanta emitted into the cold bath, so which is directly linked to the heat, which is characteristic of the detection from 2-level emitter in quantum optics. And if we compare work and heat, we can see that their mean values are proportional up to the ratio of the energy of the quanta, but also for these long integration times, their fluctuations are proportional as well, which was quite a surprising result, because well, they are different in nature, and we used different derivation path to arrive to these quantities. And then we can see that, well, in the end, yes, their fluctuation are indeed relatable by just a proportionality. Okay, so then we had these tools of we used these 2-time correlation functions, and we wanted to see if we can actually use those tools to say something about the dynamics within the engine beyond these average values. So we did it, and if we, for example, take the 2-time correlation function of the emission into the cold bath, so we record one emission and then we record another one at a later time, we can see that, well, first, this emission is anti-bunched, which means that we have to wait for a while until, if we record one emission, until we can record another one. But then we can see that if we lower that coupling, we see those oscillations appear in our correlation function. And if we look at, for example, the 2-time correlation function from the emission from the hot bath and the current, we also see those oscillations. So we see that there is another delay here, which is basically the time that it takes for the excitation to go through this part of the engine, but also oscillation that goes to positive and negative values in current. And same if we look at the correlation function from the current to the emission into the cold bath. And for us, this meant that, well, basically when we reduce the coupling to the bath, when we isolate the system, the quantum of heat actually doesn't go through the system directly. It oscillates back and forth and stays trapped in the system until it is completely released. So even though we have a positive current production on average, this is actually not what dynamically happens. And if we look at the two-time correlation function for the emission from the cold bath and emission from the hot bath, emission into the cold bath, we can see exactly the same behavior. So that was interesting for us because we could actually see that underneath that average value of the current, which is positive if the engine is working properly, it's not actually just a steady, constant positive current. We see these oscillations in the operation of the engine. Okay, but then we wanted to see if we could improve our engine a little bit, because those, if we want to implement those experimentally, those devices are quite small, and there is a risk of leakage from the baths, which would decrease the efficiency of the engine. So we wanted to see if we could get rid of the bath and still have a good positive production of work. So we modified the engine, we took the same engine as before, but instead of having heat bath, we have a measurement protocol, and we use projective measurements in a rotated basis with respect to the qubit basis. And first, so how the way we did those measurements is by measuring one side first. So here I'm showing you the hot and cold, but we also did cold and hot. So we measure one side first. We let the system evolve with this master equation, which only involves the Hamiltonian part here because we don't have any heat bath anymore. And then we measure the other side, we let the system evolve, and we repeat that procedure for a number of cycles. And to test if our measurement protocol was actually good or not, we derived the periodic steady state of the system, which is the state that will reproduce itself at each cycle, but also the state that the system will reach after a long operation time. And we could see that if we use unselective measurements, so if we measure but we forget about the result of our measurements, it doesn't matter which state we start, and it doesn't matter how we measure it, either with a high frequency or by reducing the excitation injection that our measurements put into our system, we always end up in a zero work production state. So we can have a little bit of work, positive work in the beginning of the operation, but then in the end, it always goes to zero. So we modified our protocol, and we tried to think of something that would allow us to have a positive work production. So we decided to do an adaptive measurement scheme. So for the hot side, we would measure in the qubit basis, and if the result was excited, we would leave the system alone, and if it was de-excited, we would actually measure it with the same projective measurement scheme as before. And for the cold side, if it was de-excited, we would leave it alone, because that's actually the case that is preferable for a current production or work production. But if it was excited, then we would measure it. And same as before, we would repeat that a certain number of times. And what we can see is that with this protocol, we could have a positive production of work that was sustainable over time. That was actually better than the case with the heat baths. And this was just an example. We just wanted to see if we could find something. But I'm fairly certain that by optimizing this scheme, one can find a better, probably an even better production of work. And that optimization protocol can actually be adapted to any engine and to any setup. So to conclude, what we did was we derived some analytical tools to calculate the heat and work that can be applied to any autonomous engine, and directly applies to any engine where those the work can be directly linked to some operator, like our current operator. And we could see that the work and the heat, even though they're very different in nature, they have, and were derived very different in a different way. They have similar expectation values and fluctuations at long probing times. And we also managed to see underneath those average value properties and see the strokes in the operation of our engine, which was quite an exciting result. But for the measured engine, we could see that, well, it is a good candidate for experimental implementation, and it can produce positive work if a good adaptive measurement scheme is chosen, and really hoping that it will be implemented actually one day. So with that, I would like to thank you for your attention. And just to let you know that we actually have an open position in our group. So if you're interested, just email John here. And this is the people who you would be working on. So if you want to join our wonderful team and have your picture in this wonderful Zoom picture, then please email John. Thank you.
Yeah, thank you very much, Katerina. So I'm going to wait for a little bit for questions. So if the others want to ask any question, I think you can either raise your hand and raise the hand option somewhere. You work out where that is, and there's also a question and answer thing at the bottom. Okay, so I can see someone raised a hand. Martin? Wait,
yeah, do you hear me?
Yeah, we can hear you.
Yeah, thanks for the very nice talk. It was very interesting. So I was wondering about the part about the measurement engine. So I don't know much about this, but okay, when I see these protocols, I mean, a very naive idea would be, I mean, I could just measure a qubit, right? And then if it's excited, I extract work. And if it's not, I do nothing. Okay. So, I mean, this naive thing, you wouldn't really need a cycle or the 2 qubits. So I was kind of wondering how it would compare to yours. I mean, could you do better by the fact that you use the 2 qubits and so on? I don't know if it's clear, the question.
Yeah, I understand. So you would measure just because, like, if you just measure one qubit, then we actually consider the case where we would measure just one side and leave the other one coupled to a bath. And then you can find a situation where you would have work production, if I remember correctly. But the thing is, it's more interesting to actually have get rid of both baths. I think in just like in an implementation kind of thing.
Yes.
But the best way, actually, it is actually better to measure both sides, because then you have more freedom in the way you measure. Like, you have more control over your system. You can control how you measure them, and you have more control over those parameters. It is actually giving you better, a higher work production if you measure on both sides.
Okay, yeah, but maybe it was more, not so much to keep one bath connected. I mean, I could also measure both sides, but somehow individually. I mean, you do kind of an adaptive scheme. So I was wondering, is by the fact that you have an adaptive scheme using the 2 qubits, this also you would gain something with respect to, say, measuring them individually. And maybe it doesn't make sense, the question.
No, it might. Actually, we do measure them individually. We don't measure them. We measure one side, and then we measure one side, and then we measure the other side. And actually, we could measure them at the same time. I didn't actually put every detail of the work that we did, but we actually changed those those times that I put here, T1 and T2.
Yes.
Yeah, those we actually changed them, and we also put them at 0. And then it's just another parameter that you can optimize to find. I just showed in the end, I just showed the optimal the optimal situation.
Yeah, and the optimal one is non-zero.
The optimal one is non-zero, yes.
Okay, yeah, then this answers my question. Yeah, thanks.
Mm-hmm.
Okay,
thank you. Short question for me. How does this compare to like Maxwell-Lehman type of setups? I mean, the adaptive case, isn't that quite similar to a Maxwell-Lehman who changes operation after learning a measurement outcome? Is it the same or different?
I guess it would be, well, I don't know if it's exactly the same, because we have I guess it is comparable, because we do ask the system if it does change, like the adaptive scheme does ask the system, like, are you in or favorable like situation or not? And then if it's not, but the thing is, if it's not, then we apply this projective measurement with this unselective measurement scheme. So we're not actually flipping the state of the system. We're not changing, so we're not asking it if you are you excited or not for the hot side, and if it's de-excited, then we will excite it. We let it we apply this unselective measurement afterwards. So I don't know if that exactly compares to the Maxwell-Lehman protocol. I don't. Does that answer somehow the question? I'm sorry.
Yeah, a little bit. Yeah, a little bit. I think in the Maxwell-Lehman, they don't do anything specifically on the system either. They just measure, and depending on what the measurement outcome was, they take different action. So I think it sounds similar to what you're doing, but I'm not entirely sure.